In lesson 4.8, we study the rates of change of a particle moving along a line. Alright, so a few things we're accomplishing today. First, we're going to define the average rate of change, define instantaneous rate of change, know how to relate between position, velocity, and acceleration, describe horizontal and vertical motion of an object along a straight line, give the conditions for when an object is speeding up or slowing down, and know the difference between distance and displacements. So first, we're going to begin by looking at how to calculate the average rate of change. So here is a table that represents time versus distance traveled. First, we're going to go ahead and compute the average distance traveled during the first 30 minutes of the trip. So we begin by labeling that. Okay, so average rate of change in the first half an hour. That means that from 0 to half is half an hour, right? So the average rate of change is defined to be the change in position over the change in time. The change in position between the first half hour will be the difference between 25 and 0 over 0.05 minus 0. This is the change in time. That gives us 25 mile for 0.5 of an hour, and we know that that equals to 50 miles per 1 hour. So the average rate of change in the first half an hour is 50 miles per hour. Okay, now second question says, can you compute how fast the car traveled during the entire trip? So that refers to the average rate of change over the entire trip, which is 4 hours. We also take the change in position. Okay, change in position divided by the change in time. Change in position during the 4 hours is 180 minus 0 over the change in time, which is going to be 4 minus 0. So that equals to 180 miles over 4 hours. And if we divide that correctly, that comes out to be 45 miles per hour. And that is the average speed over the last 4 hours. Now, can we determine how fast the car was traveling at a particular moment or instant in time with the information provided? So say if I want to find out how fast the car was traveling at the end of the first hour, at that exact moment, the answer is no, we cannot. Not with the information provided, because in order to do that, we would need to find. So to answer this question, no, because exact speed is derivative, and we do not know the function. Therefore, we cannot find derivative. Since we don't know the function that represents this specific model, we cannot find the derivative, which means that we cannot find the speed at a point. Okay. All right, so average rate of change, we calculated the average rate of change on the other page. It is defined to be the change in position divided by the change in time. Another way to say the change in position is to say displacement. Another way to say the change in time is time that has passed, so elapsed time. Okay, that's how we define the average rate of change. Displacement divided by the time elapsed. The change, or we can also say as the change in y over the change in x. Displacement can also be thought of as the change in the s function, if s represent your position function, over the change in time. Okay, the change in y over the change in x, we can represent that with like f of x sub 1 minus f of x sub 0 over x sub 1 minus x sub 0. So this is the change in x. Graphically, the average rate of change is the slope of the secant line. That is the average rate of change over a span of time. Okay. Distance, when we refer to distance, we're referring to a quantity that measures the length over the entire path. Distance. Okay. Displacement, however, is just the change in position. So to give you to help you understand the difference between distance and displacement, assume that each of these segments is 5 units long. Okay, say you started here and you're going to be moving this direction. Now once you stop here, then your distance from the starting point would be 5 units, and your displacement will also be 5 units. Okay, say if you continue to move around this path, okay, and once you ended up at this corner, then your distance would be 10 units, and your displacement would be the change in position. So this would be your displacement right here. And clearly your displacement is different than your distance because it's the change in position. Turns out that this is about 5 root 2. Okay, as you continue to move down, okay, say once you have now landed at this point, then your distance would be 15 units long, but your displacement is only 5. And as you continue to move to the left, and now you're at your official ending point, once you're here, then your distance would be 18, but your displacement would only be 2. So there's a difference between displacement and distance. Displacement is just the change in position, your starting position and your ending position, while distance is the quantity that measures the length over a span of time. Okay, so we discuss about average velocity. We discuss about the difference between distance and displacement. Now we get to the nuts and bolts of this lesson, and that's the instantaneous rate of change. In other words, speed at a moment. Speed when you glance at the speedometer, just a quick glance at it. Or say if you're driving along the road and you take a snapshot of the speedometer, how fast are you driving? That's instantaneous speed. So to find instantaneous speed at a time, we use the derivative, which by definition it equals to the limit as x sub 1 approach x sub 0. So we're going to take this time to be we're going to drive x sub 1 really close to x sub 0. So x sub 1 will nearly be the same as x sub 0. And this is how we define the derivative, right? Which in our case now, this is just the instantaneous rate of change. That's equal to that. Okay, they mean the same thing, they just have different function name. The symbol that we use to represent this is just f prime evaluated at x sub 0. The symbol that we use to represent that is s prime evaluated at t sub 0. This represents the speed. Now, we don't use this notation to find the speed because using definition to find derivative just takes a lot of time. So we use the shortcut or the rules that we have established in class. Graphically, instantaneous rate of change is the slope of the tangent line at a particular time. Okay. Now, you might be asked to find the instantaneous rate of change, which is the derivative at a moment in time. Bottom line, instantaneous rate of change is the derivative at a moment in time. So now we look at the relationship between position, velocity, and acceleration. Position could be represented as s sub t, or sometimes you might see them write it as f of x. That could also be used to represent position. Velocity function is called v, but to find velocity, you just take the derivative of the position function. Acceleration is represented by the letter t. To find acceleration, you take the derivative of the velocity function, or we can think of it as the second derivative of the position function. Now, this is just to make sure that you understand these terms correctly. When you hear average velocity, I want you to think of the average rate of change. And remember that from the previous page, this is the change in position over the change in time. And recall that the change in position is represented by s of t of 1, take away s of t of 0, divided by the time that has passed. This is the average velocity or the average rate of change. Same thing, okay? However, when we say ask to find the average acceleration, then this is the change in velocity over the change in time. That will give you the acceleration. The change in velocity is acceleration, right? So we calculate that by taking the change in velocity over the change in time. That gives you acceleration. Okay, so graphically, average acceleration is the slope of the secant line on the velocity graph. In other words, say if this was the graph of the derivative, okay, then if we calculate the secant line, say between those 2 points, then the value of the secant line is the change in acceleration, or the average acceleration. Speed is defined to be the rate at which an object is moving. Okay. Speed is very similar to velocity. If you can find velocity, then you can find speed, because speed does not have direction. It's just a positive number. However, velocity has direction. Say if velocity was positive, that means you're moving to the right, and if velocity is negative, that means you're moving to the left. But speed doesn't have direction, okay? So to find speed, you just take the absolute value of the velocity, and that gives you speed. Okay, so keep in mind that velocity is represented by v of t or s prime of t. That is velocity. Speed is the absolute value of either one of those, and that is speed. Okay? Motion along a straight line. So say if you have a particle that's moving along a straight line, okay, particle could be moving this way, right? Or it could also be moving, that way as well. So all it does is it moves along a straight line, and its movement sometimes could be very random. But here's what I want you to know. In order for you to determine whether or not the particle is moving to the left or to the right, you look at its velocity. If the velocity is positive, then you know that the object is moving to the right. And if the velocity is negative, then the object is moving to the left. And recall that velocity is like the first derivative, right? So if the first derivative is positive, that means that the object is moving to the right. And if the first derivative is negative, that means that the object is moving to the left. That's horizontal linear motion. We also have what's called vertical linear motion, which now the object, instead of moving left and right, it's actually moving up and down. So say if you have an object that either moves up or moves down, okay, then we can describe its motion if we're able to determine its velocity function. So once again, if velocity is positive, then the object is moving up, and if velocity is negative, then the object is clearly moving down. Okay. All right, so as a particle moves either left, right, up, or down, there could be times when it is speeding up. Think of it as when you're at a red light and all of a sudden the light turns green. What do? You're moving forward, and you also are increasing your speed, so you're speeding up. Now, you could also be slowing down, especially when you see a red light. Before you come to a stop, you have to slow down, right? So to know when a particle is speeding up or slowing down, we have to look into its velocity and its acceleration. Remember that velocity is represented by the first derivative, and acceleration is represented by the second derivative. Okay? So if both velocity and acceleration have the same sign at that time, either both positive or both negative, then the object is speeding up. So you have to check the velocity function and the acceleration function. If they are both positive, then the particle is speeding up. If they're both negative, then the particle is also speeding up. Okay? Slowing down is when they act in opposite direction. So if the velocity and acceleration have different signs, then the particle is slowing down. So let's say this is an example of different signs, particle is slowing down. Okay. All right, so consider the following scenario. A student walks away from the origin to a displacement of 8 meters in 10 seconds. So the student started here. This is 0 meter, and then walked away, and now the student is right here, which is 8 meters away. And it was 10 seconds, in 10 seconds. What happens next is the student stood there. The student then stands still for 10 seconds. So the student stayed here for 10 seconds. And then the student walks 4 meters towards the origin in 4 seconds. So 14 seconds, the student is now here, which is at 4 meters. Okay. The student stands still for 6 seconds, so the student remained here for 6 seconds. Then the student walks away from the origin. So walk away, this is the origin, walk away from the origin, so it has to go this way, to a displacement of 14 meters in 5 seconds. So the student will be walking away so that the student's new position is 14 meters from the origin. So the student walked this way, so now she is 14 meters from the origin. Okay? This would be kind of like a graphical image of how the particle moved over the last 35 seconds, how the particle is behaving, right? So at the 35th second, here's where the particle is. Now, one thing we can do is we can kind of model the position of a particle with a graph of displacement over time. Keep in mind that the particle, a student walks away from the origin to a displacement of 8 meters in 10 seconds. So in 10 seconds, the student started here. In 10 seconds, the student is now 8 meters away. Okay. That would be a graph. This segment right here would be a graph that models the displacement of the student in the last 10 seconds. Now at the 10th second, the student stood still for another 10 seconds. So displacement is still just 8. Okay, this is displacement. The height, this is position 0, right? The student stood still for the next 10 seconds. This is still just 8 meters away. The student did not move. The student walks 4 meters towards the origin in 4 seconds. So in the next 4 seconds, the student moved closer to the origin. So remember, the origin's right here. We're looking at just the y value, okay guys? So the student moved closer to the origin. We're not talking about this distance, okay? We're talking about this height, just the height. So right now, the particle is only 4 meters from the origin. The student stands still for 6 seconds, so in the next 6 seconds, he did not do anything, or she did not do anything. And then eventually walk away from the origin to a displacement of 14 meters. So walk away in the next 5 seconds. Okay, in the next 5 seconds to a displacement of 14 meters. So her final position is 14 meters away from the origin. So we're looking at, again, we're looking at this vertical distance. Okay, this is the displacement. This was the position before the last, which was 4. This was 4 units. Okay, this height right here is the displacement. All right, so this models the change the position over time. We can use this graph to sketch its derivative, which is the velocity. So we say that the student, if we calculate the slope over the last 10 seconds, the slope of this segment, it is rise of 8 over 10. Rise of 8 over 10 is about 0.8. So 0.8, so you go to 0.8, and then you draw a line. Okay, that would represent the velocity of the particle. So in the first 10 seconds, the particle was moving at 0.8 meters per second. And then between time 10 to time 20, in the next 10 seconds, the particle didn't do anything. So in the next 10 seconds, the particle stayed at rest. What does that mean? It means that velocity is 0 because it stayed at rest. And then in the next 4 seconds, after time 20, the particle went backward, right? The particle went backward. If we calculate the slope of this segment, the slope of this segment would be 4/4, which is -1. So the particle was traveling at basically -1 meter per second. And since velocity is negative, the particle is walking toward the origin. Once it ended, it stayed there for another 6 seconds. If it stayed for 6 seconds, that means it's not moving. So we sketch the velocity graph where velocity equals to 0 because it's not moving. And then finally, at the 30th second, it continued to move 14 meters. It continued to move about 10 meters in 5 seconds because it currently was at 4, and to get to 14 it has to move 10. So it moves 10 in 5 seconds. That means that its speed was 2 meters per second, and there it is. Its speed, its velocity at the last 5 seconds. Okay, so this would be the velocity graph. Again, how I graphed this was I found the derivative of each one of these segments. Derivative of this is 0.8. Derivative of that is 0. Derivative of that is -1. Derivative of that is 0. Derivative of that is 2. That's how I graphed that segment. Alright, so here is the last problem and the last in the last set of information and general information that you're going to need. Keep in mind that when an object is at rest, when we say at rest, it means that velocity equals to 0. If the speed equals to 0, the object's not moving, therefore it's at rest. Keep in mind that velocity equals to 0 would mean that s prime equals to 0 because that's velocity. Or sometimes you might see something like this. Okay. X stands for the time when the velocity is equal to 0. So if whenever you find the time such that the derivative equals to 0, that tells you that the particle is at rest. The maximum height of a ball being thrown into the air occurs when the maximum height occurs always refer to time. So the height occurs when the derivative equals to 0. Because remember that maximum, right? Maximum occurs when the derivative equals to 0 or undefined. Because maximum height always occur when there is a critical point, and the critical point is the point where the derivative equals to 0. And notice that these two are somewhat related. At rest will always refer to a moving particle. A maximum height always refer to like a ball being thrown in the air. Okay, they both are the same. You can find when the particle is at rest, when there's a maximum height, pretty much the same way. Okay. If an object is dropped, its velocity is negative because it's moving down. Okay, so expect velocity to be a negative. When an object is in vertical motion, hits the ground, when an object hits the ground, then keep in mind that its position equals to 0. Because if the position equals to 0, then it hits the ground. Okay? think of a graph that maybe looks like this, okay? Say if this is the s of t function, when the object hits the ground, its position equals to 0. Okay. If asked when or at what time or how long, our answer needs to be a time. Okay. If asked to find the speed, velocity, how fast, what is the rate, or for a rate of change, our answer needs to be a ratio. So you want to go 20 miles per 1 second, etc., etc. Okay. All right. So here's our last example. Let x be a function. Let x of t represent the position of a particle traveling along the x-axis, where t is given in seconds and x of t is given in inches. So this is the x-axis. A particle is moving along the x-axis, okay? And so here are the questions. Find the position of the particle at time 1. So position of particle at time 1 is x of 1. That gives you the position. So you just plug 1 in there and you find the position of the particle at time 1. So we take 1, we raise that to the 3rd power minus 1 squared minus 18 times 1 plus 30, we end up with 12. So at the end of the 1st second, its position is 12. Okay. Find the velocity at time t. Velocity at time t is derivative. So we go x prime of t, which equals to 3t squared minus 2t minus 18. That is velocity at time t. This is the velocity function for any time t. Okay? What is the velocity after 2 seconds? This stands for the velocity after 2 seconds. We plug 2 in there and we find the velocity after 2 seconds. 2 squared minus 2 times 2 minus 18 gives us negative 10. So negative 10, perhaps negative 10 meters per second. Okay. When is the particle at rest? Particle is at rest when x primes of t equals to 0. So we find its derivative and then we set it equal to 0. We did find its derivative in part B, so now we set it equal to 0, and then we solve. Okay, to make it fast and simple, I'm going to solve it using a calculator. The way how I do that is I graph the function and I want to see where it crosses the x-axis. Notice that it crosses the x-axis there. I don't want to take negative time, so I'm going to take positive time. So 2.805 time. This is the time where the particle is at rest. Okay. notice that before this time, the velocity is negative, so it was moving to the left, came to a stop, which is at rest, and then continued to move to the right. E, when is the particle moving in the positive direction? So this is where I'm going to create the sign chart. From what we did here in D, we found where the particle is at rest, but that's also a critical point. Okay, this is where the particle is at rest. From the graph, we know that to the left of that blinker is negative and to the right is positive. So when is the particle moving in the positive direction? The particle is moving in the positive direction at time the particle is moving in the positive direction where this is positive, so that would be 2.805 comma infinity. When that's positive, it's moving in the positive direction. Okay. Find the acceleration at time t. Acceleration is the second derivative, so we take the derivative of that function. Okay, x double prime equals to 6t minus 2. That's the acceleration function. When is the acceleration positive? So we need to set it equal to 0. And we find the time when the acceleration is 0. We create a number line. One-third. We pick a test point, so let's pick a point to the right of 1/3. That will give you positive. Pick a point to the left of 1/3. That should give you negative. Okay, so we can now answer the question: when is acceleration positive? Acceleration is positive between 1/3 and infinity. So after 1/3, acceleration is positive. Is the speed of the particle increasing or decreasing when time equals to 2? So to determine whether or not the particle is increasing or decreasing, we need to find the velocity at 2 and derivative at 2. Now, at 2, you can look at the sign chart and quickly tell. So at 2, clearly velocity is negative. So velocity at 2 is negative, right? Because 2 is right here, negative. Acceleration at 2 is positive, because 2 is going to be out here. So acceleration at 2 is positive because velocity and acceleration have different signs. The particle is slowing down. So speed is decreasing because velocity and acceleration have different signs. Find the total distance traveled by the particle during the first 3 seconds. Find the total distance traveled by the particle during the first 3 seconds. Go ahead and skip the last part, which is part I.